Hello! So in this video, we are going to continue our discussion on heat transfer. And let's start by reviewing the states of matter. So we learned this a long time ago, but just as a refresher, we know that a gas is a state of matter in which atoms or molecules have enough energy to move freely. So we have a gas in this far right container here. And those particles in the gas or molecules have a lot of energy. So the particles or molecules are constantly moving around. And therefore, they take the shape of the container that they're in. And they don't have a defined volume. And then a liquid is a state of matter in which atoms or molecules are constantly in contact, but they have enough energy to keep changing positions relative to one another. So liquids do have a defined volume, but they do also take on the shape of the container that they're in. And then a solid is a state of matter in which atoms or molecules do not have enough energy to move, and they are constantly in contact, and they're in fixed positions. So solids have a defined shape. They do not take the shape of the container that they're in, and they have a defined volume as well. Now, we also know that we can change a state of matter by adding heat or removing heat. So for example, if we start with ice, we can melt that ice and turn it into a liquid. And we can do that by adding heat. And then we could keep adding heat and turn the liquid into a gas through evaporation. Now we could go the other way. We could decrease the temperature of our gas or remove heat from the gas, and it's going to cool back down or condense into a liquid. And then if we keep removing heat from our liquid, so we decrease the temperature, eventually that liquid will freeze back into a solid, in this case, ice. Now, there is a special case where you can skip the liquid phase and go straight to the gas phase. For example, if you've ever used dry ice before, that's solid carbon dioxide, and you can just buy this at your local store. But dry ice skips the liquid phase and it goes straight to the gas phase. So that would be called sublimation. And then if a gas turns straight into a solid and skips the liquid phase, we call that deposition, which always just makes me think of lawyers, but okay. Now, let's talk a little bit about some new terms to describe adding heat and removing heat. So these terms are endothermic and exothermic. So if we add heat to a substance, that process is referred to as endothermic. So endo essentially means into. So in this instance, heat is going to increase the speed of the molecules and cause them to move faster. So for example, this would be turning a liquid into a gas. We're going to add heat to the liquid and eventually it turns into a gas. Similar to if you boil water, it turns into steam. Now let's say we remove heat from a substance. That process is referred to as exothermic. So exo essentially means out of. Okay, so in that instance, heat is decreasing the speed of the molecule, so we're removing heat So the speed of the molecules is decreasing, and therefore they're going to move slower. All right, so I have some examples again down below. If ice melts, that means we're adding heat. So heat's going into the ice and melting it. So that would be endothermic. But fire is going to release heat to its surroundings, right? So that would be exothermic. Okay, so let's apply this to something called a phase diagram. All right, so we've got our phase diagram that I showed you at the very beginning of this chapter. And remember, on the x-axis, we have heat being added to our substance. On the y-axis, we have the temperature scale in degrees Celsius. Okay, so initially, we have a solid, and we're going to assume that this is below the freezing point of water. So that would be 0 degrees Celsius. So our water molecules are frozen, they're stuck in place. And as we add heat, the temperature of that ice is going to increase until we hit the melting point, which is also referred to as the freezing point. So those are the same thing. At the melting point, what's really interesting is that we're going to have a mixture of solid and liquid. So the ice is going to start to melt, so we start to see some liquid forming. But notice that the temperature doesn't change in this region. It just stays at 0 degrees. So the energy that has gone into the solid is now no longer increasing the temperature of the object. So now we're just melting the object. Now once everything turns into liquid, then we're going to notice the temperature increase again, going up towards what's called the boiling point. So this is where the liquid would start to boil. And for water, this is at 100 degrees Celsius. Now, notice again, while the water's boiling, we have a mixture of liquid and gas, and the temperature isn't changing anymore. So again, that temperature stays the same during the boiling process until everything has turned into a gas, and then the temperature increases again. So, very interesting how energy works and how heat transfer works. Now, the equation that we saw earlier said that heat is equal to mass times the specific heat of the object times a change in temperature. So we can apply this change in temperature equation here to the parts of the phase diagram where temperature is actually changing, but we can't apply that to the melting point or the boiling point. So if we want to figure out how much heat is transferred during the melting point and the boiling point, we have to use different equations. All right, so let's figure out what those equations are. Oh, this slide just kind of walks through what the melting point is, what the boiling point is, and basically what I just talked about on the last slide. But if you need these for your notes later, feel free to pause the video and write these down. All right, so let's talk about the first equation we'll use, which is called the heat of fusion. Okay, so for each phase change of a substance, so for example, going from solid to liquid, there is a characteristic quantity of heat needed to perform the phase change per gram or per mole of material. So the heat of fusion, which is given this symbol here, delta H with a subscript FUS for fusion, this is the amount of heat per gram required for a phase change that occurs at the melting point. So heat of fusion is used for the melting point specifically. All right, so I have two equations down below. One where heat is equal to mass times this heat of fusion value, and we'll talk about that in a second. Or you could also write this in terms of moles times the heat of fusion. So it just depends on what you're given. Okay, now let's look at the boiling point. What equation do we need for the boiling point? Because we've already talked about melting point. So at the boiling point, instead of a heat of fusion, we use something called a heat of vaporization. So again, this will be for the boiling point. So the symbol for the heat of vaporization is delta H VAP. And again, this could be written in terms of mass or moles, and moles is given the symbol N. Okay, so why do we need two different equations? Well, down below, you'll notice that the heat of fusion at the melting point for a particular substance is different than the heat of vaporization at the boiling point. So different amounts of energy are needed to melt something versus boil something. And that makes sense, right? It's super easy to melt a piece of ice. It can just melt in your hand, right? But it's really hard to boil water. And we talked about that before. It takes forever to boil water. So melting ice doesn't take very much heat, but boiling water takes a lot of heat. So we have different constants for those two different points. And down below, you can see for water, delta H fusion, so the melting point value, is 79.9 calories per gram of water. So it takes about 80 calories of energy to melt a gram of ice. But if we want to boil that same amount of water, we need 540 calories of energy. So that would be our heat of vaporization. So that's a lot more energy we need. So that's why we have two different equations. So let's actually go back to our phase diagram. So now we know that for the melting point, heat is equal to mass times the heat of fusion. And for our boiling point, heat is equal to mass times the heat of vaporization. And again, those are values you can look up in a table, and I would give those to you on a test. Okay, so now we have everything we need in order to calculate how much heat is transferred from this point at the bottom of our graph all the way up to this point at the very top of our graph. So that's pretty cool. We can actually calculate how much heat is needed for that entire process. We would just have to break it down piece by piece and use a different equation for each section. Okay, So let's practice using these two equations we just learned about. So how much heat is necessary to vaporize 685 grams of water at 100 degrees Celsius? And the heat of vaporization of water is 540 calories per gram. Okay, so right away we're given the heat of vaporization. So this tells us that we need the equation where heat is equal to mass times delta H of vaporization. And luckily, we're given the mass, 685, so let's plug that in. And we're given the heat of vaporization, 540 calories per gram. Now we're also given the temperature, 100 degrees Celsius, but that's sort of extra information because remember the temperature doesn't change during boiling or melting. It just stays the same. And our equation doesn't include temperature for this part of the phase diagram. Okay, so looking at our equation, we're going to cancel grams and we're left with calories, which makes sense because we're calculating heat. So we just have to multiply 685 by 540. And initially my calculator gave me 369,900 calories. But how many sig figs should we use for this equation? So it looks like we're given 3 sig figs for the mass, but only 2 sig figs for the heat of vaporization. We don't have a decimal on the end, so it's only 2 sig figs. So let's limit our final value to 2 sig figs. So let's just round up. So this will be 370,000 calories. Now remember, you could also write this in scientific notation. So that would be 3.7 times 10. Let's see, to the 1, 2, 3, 4, 5. So 3.7 times 10 to the 5th calories. Okay, so let's do one more practice problem. How much heat is necessary to melt 55.8 grams of ice, which again is solid water, at 0 degrees Celsius? The heat of fusion of water is 79.9 calories per gram. So see if you can do this problem on your own. So pause the video, try it out first, and then when you're done, you can unpause and we'll go over it together. Okay, so since we're given the heat of fusion for this problem, we're going to use the equation where heat is equal to mass times delta H of fusion, or heat of fusion. So we're given the mass, so let's plug that in. And we're given the heat of fusion, so we'll plug that in as well. And just like before, grams will cancel. And we're going to get, let's see, my calculator gives me 4,458 calories. But how many sig figs should we have? So the mass, we're given 3 sig figs, and heat of fusion has 3 sig figs. So let's round this to 3 sig figs. So we should get 4,460 calories. Okay. So not too bad, right? And on an exam or a quiz, I will give you those equations we've learned so far. So the first one where heat is equal to mass times specific heat times the change in temperature. And then these new ones where heat is equal to mass times either the heat of fusion or heat of vaporization. Okay, now in the next video, we'll go over energy and chemical reactions. I will see you then.